compact quantum groups. Can you see what I show?
Yes. Yes.
Yeah. So good. First of all, I want to discuss a little about general notion of quantum groups and how we get them. When we consider a group, we can define point-wise algebra of functions defined in that group. So that algebra defines on what we have at a point, and we have addition. It is well-defined addition, multiplication, and people build get classical groups, and from that groups build commutative algebra of functions on that group. The strategy of getting quantum groups in general is to forget about the group, make some deformation, make some changes which change our algebra to non-commutative, and with a better non-commutative algebra we will associate quantum group. So for quantum groups, there are a few approaches of considering functions on a group, and it depends on the algebraic or geometric structure of that group. So usually on algebraic groups, people consider algebra of polynomial functions, and that approach developed Woronowicz and Greenfield. On topological groups, it's natural to consider algebra of continuous functions. It considered Woronowicz, and Greenfield considered formal power series defined on a group. So,
for which groups do we consider formal power?
Formal power series. If I understand right, it can be for topological and algebraic, but I'm not sure.
Probably you mean that when you speak about formal power series, you consider formal deformations of, usually we consider formal deformations of universal enveloping algebras. So we start with the Lie algebra, and we take the universal enveloping algebra, and we try to somehow quantize it. And this leads to its formal deformation, which is an algebra over the ring of formal power series.
Yes, yes.
So so basically, it's the natural approach for Lie groups.
Or more exactly, for Lie algebras.
Yes, and I want to highlight that actually the third approach is very important for applications. That approach uses in conformal field theory, in integrable systems, but the first, which we are going to talk about, the first approach and the second people usually when talk about quantized space-time, space, and this approach is important to that. Investigating quantum groups is important due to applications, because people in mathematical physics, people still dream about union of quantum mechanics and general relativity, and one of ideas that near black holes it's worth to consider non-commutative space-time space operators because of Heisenberg principle of uncertainty, and it is motivation, some motivation for what we are going to do. So in our discussion, we will consider polynomial functions on algebraic pools group, and we start with such abstract notion as Hopf algebra. Now I understand that definition in detail. So it's a big picture, and I like it because it shows inner structure of Hopf algebra. Hopf algebra, it's on the one hand, it is algebra. We have a unit, we have a multiplication. We suppose that there is unit in our algebra, and for that algebras, we demand two axioms. It's associativity and consistency with union. Also, Hopf algebra should be co-algebraic. It means we should have co-unit and well-defined multiplications. Notice that multiplication should be bilinear and multiplication linear.
Shouldn't there be a tensor product instead of Cartesian product?
Probably I missed one important thing, that we consider Hopf algebra we define for complex vector space. So for complex vector space, we can define tensor product. Or you ask about a multiplication that change direct product on tensor. Yes.
And the same, the same for the multiplication, probably. When you write your identities 1 and 2, you probably assume that mu is defined on the tensor product of A by itself.
Okay. It might be a mistake. You should correct it. Thanks.
And also probably, by the way, in relation 2, we should also write that these two maps are, each of them is equal to the identity map on A. Is that correct?
Yes, it's correct. It's correct. Right. Okay, so we have algebra structure, we have coalgebra structure, and algebra, which in the same time algebra and coalgebra names bialgebra. I wrote some axioms of consistency with operations we have, and that axioms just for consistency of operations. And to form Hopf algebra, we should add the antipode mappings on our algebra, which should be linear. And in the article I read, it was enough to define axiom 9, but probably I'll add the successive axiom 10, but it's okay. And this antipode mapping should be antimomorphism, and there is proposition, but if it exists, it is defined uniquely. So, are there any questions? Is it clear?
I can also add that in relation 4, again, both maps are equal to the identity map of A.
Yes.
Similarly to axiom to property 2. So both in 2 and 4, both maps are equal to the identity map.
Mm-hmm. Yes. So we gave definition, and it's worth to consider some example. We start with simple, with finite group, and one why we start with that example, because it simply define associate algebra functions on direct product of groups with tensor product of functions algebras. We make it I'll show on slide that we take multiplication, we consider pointwise multiplication, and we generalize it that take function on direct product of our group, and just use the same argument for it. Co-multiplication we can define as taking value of our function on the products of elements of groups or finite elements of groups. Co-unit we will accept as a value on a unit element, and antipode mapping we can define as taking the value of function on the inverse element of our group. All axioms above naturally fulfilled, and yeah, for that case, and if we want, we can check something, but it seems that example clear. Another important example is algebra of functions for special linear group, and it's important example for all our discussion. So we consider complex valued functions which are polynomials and elements of matrices, and one of the reasons it's also well-defined algebra functions on a product and algebra functions on tensor product of algebras. For polynomials, it is fulfilled. Co-multiplication, so that algebra we define as taking a value on the product of elements, and x, y, it's a product of two matrices, and we take EJT element. So we can get the following view for computing co-multiplication, and we can represent it in such a way. K-unit and antipode mapping on the slide. The big T EJ is it is a complement minor for element of matrix. The algebra of polynomial functions on any subgroup of special linear group is a Hopf algebra. And now I now move forward, and Hopf algebra will name Hopf algebra for which co-unit and co-multiplication star homomorphism. And one of very important properties of that algebra is that for that algebra, the following identity is fulfilled. It is the first hint on for definition of compact quantum groups according to Woronowicz. So for Woronowicz algebras, for Woronowicz compact quantum groups, it's one of criteria which should be on them, and that identity is fulfilled. That proposition proves by using axioms which we gave, and we should also, to prove that, we should also define inverse multiplications. It's multiplications which transpose elements, inverse multiplication which transpose elements of multiplication. So this proposition is important. Examples of Hopf algebra. Simple is finite groups with star for which star homomorphism is just complex conjugates. For subgroups of real special linear group, we can define star mapping the following way and make antilinear holomorphic continuation. The next example is more interesting. It's when we take subgroup of special unitary group, and we defined star mapping by the following way, and we see the relation between star homomorphism for elements of star algebra and antipode mapping. After that, we make antilinear homomorphic continuation for overland elements. Are there any questions? Now we'll talk about corepresentations of algebra. It's defined on a linear space, and it's a mapping such that take elements of our space and maps it into a tensor product of our space with our algebra. For such mapping should be fulfilled two properties, which I wrote. So in simple case, when we deal with finite dimensional space, we can choose basis and define corepresentation on elements of that basis. Obtained matrices will name matrix corepresentation of algebra. So in that simple case, we can just compute how commultiplication acts on elements of on corepresentation and how it looks. For that we just use a definition of corepresentation, and that's all. Example of corepresentation. Also, we start with our favorite example of finite groups. For finite groups, let's consider finite group. For finite groups, is well defined their representation, and we can define a tensor product of our space, space on which the space of presentation and algebra functions on our space, so that link expressed by that arrow, and corepresentation will name the resulting element of representation or element x. X is element of our finite group, and that matrix via x acts on element of our vector space and give another. So it will corepresentation of algebra of coalgebra functions on vector space And for that case, axioms of corepresentations are fulfilled, and the result of their implementation, so we can show on the slide. So we had two axioms, axiom 1 and 2, and for finite case, it just will multiplications of different multiplications of matrix operators for elements x and y, and representation of multiplication elements of our group. For SL, for special linear group, our corepresentation can be defined in the following way. This way is important. Proposition for matrix corepresentation of all algebra. The following relation is fulfilled. It is the second hint on the definition of compact quantum algebras according to Woronowicz, and this the second important relation, and it has easy proof. So we just rewrite the left side of equality in the following way. Then we should remind the definition of commultiplication, which has led the slide for finite case. When we should axiom Hopf algebra and get the necessary relation. Unitary corepresentation we will name. We will define for Hopf star algebras, and we will associate with result of star homomorphism to matrix corepresentation. The antipode mapping of transpose corresponding matrix. This definition is consistent with what we discussed earlier. So when we chose a subgroup of special orthogonal group, we get the similar relation. And that relation we will take for ground, and for unitary representations, following proposition is right, that is unitary corepresentation. Here is mistake, here mistake, and for unitary corepresentation, we can define the following decomposition of unit element of our algebra. Corepresentations. Corepresentation has invariant subspace W of V with the subspace is invariant if the image of representations lies in the tensor product of that space with the whole coalgebra on our defined on our vector space. And the representation is reducible if it has only two invariant subspaces, the whole and 0. The theory of corepresentations is very similar to the theory of just simple representations. For that, we have also the fact that subspace is invariant and orthogonal complement is also invariant. So we also have the fact that direct sum of invariant subspaces that we have decomposition on the irreducible representations of A. For that theory is also defines interviewing operator, and there is also another Schur's lemma, and that theory is closely connected with just usual and traditional representation theory. Now we move to the notion of quantum compact group. It's defined for Hopf-Star algebra, and we say that Hopf-Star algebra associated with compact quantum group if it's linear span of matrix elements of unitary matrix representation of A. And then A we will name CQG algebra. We will use the following notation for reducible unitary for definite reducible unitary representation of A, and define I alpha as a span for representation. If our CQG algebra is finitely generated, when we name it compact matrix quantum group, we will name that it is associated with compact matrix quantum group, and A we will name CQG algebra. For that algebras, we can define linear mapping Haar functional on CQG algebras. It takes element of our algebra and maps in 0 and our unit if A is unit 0 or otherwise. That functional is very important, and the theory connected with Haar functional is connected with Peter Wade theory, And Haar functional, in that case, it connected with Haar measure, which we have defined for compact groups. And to proceed to investigate that theory, we should do that functional. And there is important theorem that for that functional on CQG algebras, the following equality is true, inequality is true. So Haar functional is positively defined on our CQG algebra. And according to that functional, we can build even scalar product. So when we define the Haar functional, after that we move to C-star completion of that algebra. And let's remind you that C-star algebra is just Banach algebra with star algebra, and in the same star algebra preserves the norm in the following way. A simple example is an example of pointed in operators on Hilbert space, and star representation will name star algebra homomorphism from our algebra into algebra of bounded linear operators defined on Hilbert space. We move to the end of our construction, and we can define a norm on CQG algebras. That norm we will define as supremum, which we take between all star representations of our algebra. And if we take, so we get CQG algebra, we define on this algebra norm. It is also not obvious that what we have norm. So we should also show that it is a norm. However, if we show that, after that we make C-star completion of our algebra according to this norm, and we move to the notion of CQG algebras according to Woronowicz. We move to the notion of compact quantum groups according to Woronowicz. Woronowicz defined that groups as a pair where AU, where A is unitary star algebra, and U matrix for which with entries in A for which three properties are fulfilled. So the star algebra we should be dense in A. We should have unique C-star homomorphism, which similar to multiplication we define. And it should have linear anti-multiplicative mapping satisfying two conditions. So as we've showed that for commultiplications infinite dimensional case, that property is true. Second, third property, and for Hopf algebras, Hopf algebras is also fulfilled, and we show the last property for that antilinear mapping. So according to Koornwinder, that antilinear mapping is just antipode mapping. The second homomorphism, according to Koornwinder, is multiplication. And the first case is the final first stage on that construction of compact matrix group is the last stage of Koornwinder approach, and now we move to the notion of compact matrix quantum groups. And it's interesting how we start. So we start just with axioms. We start with algebraic approach. We start with algebraic approach, define some axioms. When we prove some properties, which turned out coincide with properties which Woronowicz demand from compact matrix groups, matrix quantum groups. And after we make that construction, we were able to define a norm. And when we make completion according to that norm, we get definitely the notion of compact quantum matrix groups according to Woronowicz. And it was the main goal of my report to show that alternative approach to that groups, and I tried to explain how we can get this. So if you have questions, you can ask. And that's all I want to say.
Well, thank you. So are there any questions or remarks?
Could you send us your presentation, please?
Okay.
You can, for convenience, you can send it to me, and then I'll send it to all the members of the seminar.
Okay, that will be better.
Well, maybe I'll make only a short comment about this definition. So this was the original definition of Woronowicz, which was given probably in his first paper on the subject. A bit later, he gave another definition, which is slightly more general, the general definition of a compact quantum group. And this more general definition doesn't involve any dense subalgebra. So what is interesting is that the existence of such a subalgebra can be proved. So he starts with the sister algebra with the co-multiplication satisfying some axioms, and then after some work, he proves that there exists a unital dense Hopf subalgebra in A, which is spanned by matrix elements of unitary corepresentations. So it is not equivalent to this definition, because here we require the here we consider only one such matrix. But if we replace here in this definition, I mean, which is on the screen now, if we replace here one matrix by a family of matrices, then we get a definition which is equivalent to the abstract definition given by Woronowicz, which doesn't involve any dense subalgebras. So, any other questions or comments?
My comment is I kind of like such a short talks because long ones are mostly impossible to follow through.
Alexei,
Your microphone.
we can hear you.
Алексей Юрьевич, вы говорите с выключенным микрофоном.
I'm sorry. I just said that if there are no more questions, then we thank the speaker. And next week, our speaker will be Ria Dogara. She will tell us something about von Neumann algebras, subfactors, and polynomial not invariants, including John's polynomial. Okay, thanks everybody.
Thank you. Goodbye.